Thank you, Bethesda, for introduction. I'm Gui Xinye. I come from a School of Information Science and Technology, Northwest University at China. Now I'm going to talk about our work, a generated adversarial network-based solver on text-based captchas. This is a work that collaborated with other co-authors from Lancaster University and Peking University. In this work, we saw that 11 captcha schemes that are being used, 32 of the top 50 popular websites can be cracked with a higher success rate than previous state-of-the-art methods. So how can we do that? Now let's begin with the introduction of text-based captchas. Text-based captchas are extensively used to distinguish humans from automated computer programs. Many websites and applications use the text-based captchas as a security and authentication mechanism. According to our statistics, about 32 of the top 50 popular websites were being used text-based captchas to defend against molecular sports. These websites include Google, Microsoft, Alipay, eBay, and many others. Given the wide deployment of text-based captchas, we're wondering that whether current text-based captchas are secure. Because breaking text-based captchas is not a new topic, so let's to review state-of-the-art methods. The mainstream state-of-the-art methods is model-based approach. This kind of approach can be summarized as 3 steps. First, give a unique captcha scheme. This method first remove the complex background over the text, and then it split each character from the image. At last, this method use machine learning algorithms to recognize each segmented capture, each segmented character. However, for a unique captcha scheme, this method requires the corresponding pre-processing and segmentation technologies. Also, for each step, it requires lots of parameters to be tuned. So, model-based approach requires extensive human involvement. On the other hand, this pre-processing methods used by previous model-based approach is filled to remove the background of bad captchas. So model-based approach is filled to identify current text-based captchas. Another widely used method is deep learning-based approach. However, this approach, as we all know, requires millions of real captchas. For example, to recapture, although its success rate can reach 89.9%, while it requires 2.3 million real captchas. And to photo OCR, its success rate no less than 2%, but it requires nearly 8 million real captchas. Also, it's time-consuming for gathering and labeling a large number of real captchas. Further, it's very difficult for collecting and labeling a large number of real captchas because most websites use anti-crawling mechanisms. Even if an adversary get a lot number of real captures. Its method is may also be evaluated because most websites use frequently change its capture scheme. So deep learning based approach is also evaluated to current text-based captures. Since it's very difficult for collecting and labeling a large number of real captures. We're wondering there is a way to solve current text-based captures. So this source inspires our work. Our work presented a generative adversarial network-based approach, giving a unique capture scheme. We first analysis its basic elements of the capture scheme. Here we call the basic element is the security feature of the capture scheme, such as the text, the background, and occluding lines on the capture scheme. Then we use the security feature of the capture scheme to synthesize lots of synthetic captures. To make sure the style of the synthetic captures is similar to the real ones, we use a small number of real captures to tune the capture synthesizer. And after generate the synthetic captures, we use the synthetic captures to train the base solver. We can use as many synthetic captures as we want to build the base solver according to the complexity of the capture scheme. Here we use 200 key sensitive captures to build our base solver. Note that the base solver is a convolutional neural network. It consists of LeNet 5 and with additional 2 conventional layers and 3 polling layers. Finally, we use transfer learning to fine-tune the base solver by using a small number of real captures. Specifically, we used the formal layers of the base solver and retrained the later layers of the base solver to fine-tune the base solver by using a small number of real captures. The tuning process is very quick because we use only 500 real captures. Here we use a generative adversarial network to train our capture to train our capture synthesizer. This kind of method, this training process consists of 2 parts. One is capture synthesizer. It's used to synthesize captures, and the other is the discriminator. It's used to identify the sensitive captures from the real ones. If the discriminator fails to identify most sensitive captures, it means that the style of the sensitive capture is similar to the real ones. So the training process will be terminated. Sorry. In the following way, I will introduce the implementation and evaluation. Sorry. In our experiment, we use 11 capture schemes that were being used by 32 of the top 50 popular websites ranked by the Alex. These websites include eBay, Google, Microsoft, Wikipedia, and many others. For each Captcha scheme, we collected and labeled 1,500 real captchas, for which we use 500 real captchas to train our capture synthesizer and fine-tune the base solver. And we use the remaining 1,000 real captchas for testing. Also, we use previous 22 capture schemes used by other previous framework to evaluate our approach. Here are some examples for each capture schemes. From it, we can see all the captures have multiple security features, such as complex overlapping and distorting character, different font styles, many occluding lines, and complex backgrounds, and many others. Here we show the overall success rate before and after tuning the base solver. From the result, we can see that all the success rates are higher than 1%, which is the threshold for which a capture scheme is considered to be effective. This presents the results when respectively comparing to other 4 previous frameworks. This slide shows the 2 comparing results, respectively comparing to CCS 2011 and DSS 2060 works. It shows that our approach performs better than previous state-of-the-art method. This is also shows the comparing result when comparing to other 2 frameworks. It also shows our work performs better. We also present how the number of real captures will affect the base solver of when fine-tuning processing. From the result, we can see 500 real captures are enough to fine-tune our base solver. Here we conclude that our approach requires less human involvement because we believe that 500 real captures collecting and labeling 500 real captures is not an annoying work. At last, we have conducted a user study to quantify the impact of security feature on user experience. We aim to find a balance between the security and the usability of the captures of the capture scheme. Here we generated 6 kinds of capture schemes to evaluate the user experience. We have conducted an online survey by recruiting 20 participants by filling to an anonymous questionnaire. In the questionnaire, we present 100 capture schemes for each 100 captures for each capture scheme, and we give our participant 1 minute to label a capture. We also ask our participant to rate the usability score. Here we also shows the success rate achieved by our participant and by our Captcha solver. From the result, we can see from the number one experiment, we can see that automated computer programs performs better than humans when targeting a simple capture scheme. From the number 3 and 4 experiment, we can see that complex background is not a secure security feature of the text-based capture. Also, a complex background will seriously influence the user experience. From the number 6 experiment, we can see the capture with complex denoted and overlapping characters may be a possible solution, but this capture scheme will seriously influence the user experience. So here we conclude that current text-based captures are not secure, considering the user experience. So balancing the usability and the security of the text-based captures is still an open valuable topic. Recently, we focus our attention to improve the security of text-based captures. Our initial experiment shows that the adversary capture generated by our unique capture synthesizer may be a possible solution. For example, the left image is the original capture, and the right image is the adversary capture generated by our capture synthesizer. They are visually no difference, but our capture solver fails to recognize the adversary captures. In the future, we will dedicate to develop a robust text-based capture scheme. Now let me conclude our talk. Firstly, text-based we conclude that text-based captures are not secure and generative adversary network-based solver. Secondly, our approach needs less human involvement and requires a small number of real captures, which is a great threat to current websites which use the text-based captures. So this is over. Thanks. Any questions?
Okay, so Yang Zhang from CISPA, Germany. So I have one question. So during your generative adversarial networks, you mentioned that you use some real captchas as the seed for your generator. Can you give more comments on that and how do you do that? Because normally the original GAN, you don't have that thing.
Yeah. I have prepared some backups later. So for a unique capture scheme, we firstly analyze its security feature, such as the text, the background, and the auxiliary lines if they have. Yeah. We use the security features to generate the captures, and to make sure the style of the captures is similar to the real ones, we use a discriminator, to identify the sensitive captures from the real ones. Yeah. If the discriminator fails to most the sensitive captures, it means that the style of the sensitive captures is similar to the real ones. Note that here we generated the sensitive capture its the style of the sensitive capture is similar to the real ones. It is not exactly the same as the real ones. Yeah. Here we use a threshold, 95%. If the discriminator fails to 95%, the sensitive captures, yeah, the training process will be terminated. Yeah.
Hi, this is Vikas from Princeton. First of all, impressive work, like the performance, and I wonder, like, with only 500 samples, you got great results. I was wondering about something like when we test this approach by moving sort of like out of distribution from what 11 captcha methods you have considered, something sort of like on the interpretability side, that if my method is not like sort of like adding black dots in my captcha, but sort of like green dots in it, well, something which is not considered, which is in the both training and test distributions, but like if I test this approach on that data set, will the performance still be intact? Something like on the interpretability sides, like what are your thoughts that if the approach is not using any of these 11 methods, will you still be as much accurate as you are on these methods?
Yeah. Do you mean how many the real captures do we use?
Yeah, something like if the test set doesn't use, I wonder, like you the approach is you set these 11 methods and create training and test sets from these samples.
Oh yeah. For one each capture scheme, we use 500 real captures to train our capture synthesizer and fine tune. You use the same 500 captures to fine tune our bit solver. Yeah.
Yeah, actually, is it off, on? Yes. Can you hear it? Okay, sorry. I'm Fabio from King's College London. I mean, maybe this was partially covered by this question, but in the test set, do you use actually real captchas or captchas generated with the GAN when you evaluate the approach?
Sorry, I don't get your.
Oh no, in the test set. I mean, when you evaluate the approach and compute the performance.
Yeah.
After the tuning, do you use like real captchas or captchas synthesized by the GAN?
Yeah, we use the same 500 real captures to to train our capture synthesizer and to fine tune our bit solver. Yeah.
Yeah, but in the evaluation.
Yeah. We use the same real captures.
Okay.
Yeah, thank you.